Hi, I'm Korhonen from the University of Copenhagen, and I will talk about dynamic Treewidth in logarithmic time. So let's start traditionally by defining Treewidth. So here is graph G, and here is a tree decomposition of a graph G. So tree decompositions are used for defining Treewidth. And to be a tree decomposition, this tree that consists of backs that are subsets of vertices of the graph should satisfy some properties. So every vertex of the graph should be in some back of the tree decomposition. Every edge of the graph should be in some back of the tree decomposition. So both endpoints of the edge should be in the back. And third, for every vertex of the graph, the backs containing that vertex should form a connected subtree of this tree decomposition. So if we look at the vertex I, then it's in these five backs forming a connected subtree of this tree decomposition. Okay, so that's a definition of tree decomposition. And then the width of a tree decomposition is the maximum backsize minus 1. So the width of this tree decomposition is 2. And tree width of a graph is the minimum width of a tree decomposition of the graph. So we know because this graph has a tree decomposition of width 2, its tree width is at most 2, and actually its tree width is exactly 2 because only forests have tree width 1. Yeah, and this definition of tree width was given by multiple people independently of each other already in the 70s and in the 80s. Yeah, so some graphs of small tree width include like trees and series parallel graphs and autoplanar graphs, while some graphs of large tree width include like the cliques or expander graphs or n times m grids. Okay. And why we care about tree width is that algorithms for trees often generalize to algorithms for graphs of small tree width. So, for example, graphs of tree width k, we can solve maximum independent set problem, which will be a problem in time 2 to the k times n. So you can think in trees, you can solve maximum independent set by various ways, and this generalizes to graphs of constant tree width or small tree width. And actually, there is this Crusel's theorem that says that all problems that can be defined in so-called MSO logic can be solved in linear time on graphs of bounded tree width. And here's one important thing that important, especially related to this work and my work, is that these algorithms for graphs of small tree width, as the first step, they actually need the tree decomposition. So the k here is not the tree width, but the width of a given tree decomposition. But this fact is often kind of ignored because we have quite good algorithms for computing quite good tree decompositions. So if you want to compute an optimum width tree decomposition, you can do it in linear time on bounded tree width graphs already for a long time. But the dependency on k is a bit the tree width. So k here is always tree width. Dependency on k is a bit large. You can improve it a bit if you want like 2 approximation. And if you want to have a polynomial time algorithm for computing tree width, then you can do like a square root log k approximation. But yeah, but not constant factor is known. Okay, so that's some short introduction to tree width, and now we go to the topic of this paper, which is dynamic tree width in logarithmic time. So now we are interested in dynamic graphs, so graphs where you can insert and delete edges. And we can ask the question, okay, when we have the situation where we're inserting and deleting edges, can we efficiently maintain a good tree decomposition of the graph? So tree decomposition of optimum width or near optimum width. And this question was asked by multiple people, by both Lander in the 90s already, and then at Porak, Kupet, and Tuma, and Olman Midge, and Vasilevska Williams Yeah, and of course, this is like an interesting question if you're looking for algorithms that run faster than just rerunning some Treewidth computation, some static Treewidth computation algorithm every time there comes an update. So we're looking for algorithms that would work in, say, a sublinear or subpolynomial or maybe logarithmic time per update. And we also would like to, so that this would be useful for as a tool. So, Treewidth is very useful for solving other problems that are not about maintaining tree decomposition, but using the tree decomposition to solve some other problems. We would also want to have this infrastructure also in this dynamic setting. So we would also like to say that this dynamic tree data structure would be nice if we could maintain some dynamic programming algorithms on top of that tree decomposition. So we would like to get this dynamic version of Courcell's theorem. And there is quite a bit of previous work even on this dynamic Treewidth question. So basically, well, Treewidth 1 corresponds to dynamic forest, which is quite a traditional topic in computer science. So we know already from the 80s by Sleva and Tarjan that you can maintain dynamic forest in logarithmic update time. It's not clear if what they have gives like a dynamic Courcell's theorem, but there are many data structures for dynamic forests, and in particular there's this top trees of Astrup, Holm, Lichtenberg, and Torup, which actually can be seen as maintaining a width to tree decomposition of trees and allowing the maintenance of like dynamic programming schemes on that, and this gives like this dynamic Courcell's theorem for sure for like for dynamic forests. Yeah, and then for Treewidth 2 there's also an algorithm by Botlander from the 90s from this paper, but it actually like he didn't the details are not written down. I have to call out him on this. And then there was much later in 2021 by Koranji, Rake, Saranaka, and Tan, their expander hierarchy paper, so hierarchy of expander decompositions, gives actually also like a dynamic tree with data structure, which has subpolynomial amortized update time, so n to the small o of 1 amortized update time. But it maintains like approximate tree decomposition, but the approximation is only like subpoly n approximation, and it works only in binary graphs. So like there's like I think like linear dependency on the degree that goes to the approximation. And this is very nice data structure for a lot of things. There's a lot of problems with it, but it's not suitable in this like this bounded tree with parameterized setting where you would like this dynamic Courcell's theorem, because the width is like only subpoly and approximate. So it's like if you put even if you have like a constant Treewidth graph, this thing can output tree decompositions with quite high width, and this explodes in the running time if you run something complicated in Courcell's theorem. Yeah. Then when 2 years ago, we actually with me and co-authors we did the first dynamic tree data structure that works for any value of Treewidth and maintains constant approximate tree decomposition. So we managed to get the 6 approximate tree decomposition with update time that is subpolynomial in n when k is fixed. So there's some dependency in k, which is quite high. Yeah, and this gives indeed dynamic Courcell's theorem in this kind of subpoly and amortized time. But of course, this leaves the question of can we improve the running time? So ideally it could match dynamic forest to be logarithmic, and this is exactly what I do in this work. So in this work, I give a dynamic tree with data structure that maintains 9 approximate tree decomposition with logarithmic amortized update time for fixed k, and also dependency on k is better than in this previous work. So it's only like only 2 to the O of k, single exponential in k. So matching like the known static constant approximation algorithms for Treewidth. Yeah. Okay, let me say some more details about this the theorem statement of this work. So the theorem statement is there's a data structure that's initialized with an integer k, so the Treewidth bound, and initially edgeless n-vertex graph G, and supports inserting and deleting edges in amortized time. This thing to the of k log n per update under the promise that the Treewidth of the graph stays always at most k, and it maintains a tree decomposition of the graph of which at most 9 times the current Treewidth plus 8. So it always maintains a constant approximation, constant approximately optimal tree decomposition, even when the width is much less than k. Yeah, and also this supports maintaining any dynamic programming scheme on the tree decomposition. So it supports dynamic Krusell's theorem and its many variants. And basically you get like this this kind of overhead. So it depends on, so this is formalized by something called a tree decomposition automata. So you can think of dynamic programming formalized by some automaton, and you can plug in this automaton to the data structure, and it maintains this automaton on the decomposition with something like this. This many transitions need to be computed per update. Yeah. And yeah, so we get dynamic Kurzweil's theorem. And maybe one thing to say here is that, okay, here is the condition that there is we need a promise that Treewidth is less than k, but this can actually be like it's not as so strict. Like it can be somewhat relaxed in the sense that well, because this maintains a constant approximate Treewidth anyway, so we can kind of detect whenever the Treewidth goes too large. So by using that, we can make this data structure so that it actually it kind of tells when the Treewidth grows too large. Like it can say, "Oh, I reject this edge insertion because after this, the Treewidth would for sure be too large." So you can make this kind of a version of it where you kind of trade off the promise into something else, into something that can be actually detected. So the promise is not that hard. Yeah, deficit here. Yeah, so that's the statement. Then I'll say something about the algorithm. So first, let me talk about what is the decomposition that we are maintaining in this algorithm. And this is actually the most important thing that we are actually not really maintaining. We're not thinking about the tree decomposition, but we are thinking about some other structure which has some and some nice invariance on that other structure. And this is like the key thing of the algorithm. Like after telling about the structure and the invariance, it's not too hard to do like the rest of the details of the algorithm. Like the main conceptual contribution of this work is actually these invariants that we maintain, and then like saying that, oh, they can be maintained is can be taken as an exercise for people who know Treewidth and know something about like maintaining dynamic trees. Okay, so what's the structure? So the structure is it's a branch decomposition. So okay, here we have our graph, and here's a branch decomposition of the graph. So here we say a branch decomposition is a rooted tree whose leaves correspond to the edges of the graph. Okay, so the edges of the graph are labeled here by A, B, C, D, E, F, G, A, H. So they are the leaves of this branch decomposition here. And here we say branch decomposition, they can have arbitrary high degree, unlike the normal definition of branch decompositions, where the degree must be bounded. And now, okay, let me introduce some definitions. So now for a set of edges of the graph, which you can think of as a set of leaves of the branch decomposition. So here, e.g. F, we say that the boundary of the set of edges is the vertices that are incident to edges from both the set F and not in this ZF. So the boundary here is this red vertices, not this black one in the middle, because it's adjacent only to something from this edges F. Okay, so that's quite intuitive notion of boundary. And then we say a set of edges F is well linked if it cannot be partitioned into two parts, so that both of the parts have a strictly smaller boundary. Okay, this is a key definition in this work. This is the main thing that makes everything work so smoothly. So for example, this is actually, it turns out this set of three edges here is well linked. You can think it's whenever you can basically, if you take one edge off, you get something with boundary size 3. You still get something with boundary size 3. Yeah, so this is well linked. Okay, and what we want to maintain in our branch decomposition is that whenever we have a subtree, okay, which corresponds to some set of edges of the graph, we want that this set of edges is well linked, and we call this property of the tree decomposition that every subtree forms of the branch decomposition. That every subtree forms a well linked set. We call this downwards well linkness. Okay, and this is the main invariant we have. And this is like the main thing that makes things work. Okay, so what does this give? So it turns out it's quite well-known property of like a Treewidth that whenever you have this kind of downwards, whenever you have this well-linked set, the boundary of it has size at most O of k, where k is the Treewidth. So if you have bounded Treewidth graph, now all these boundaries have size O of k. Okay, it's the Treewidth. Yeah. So now you can, how we think about this now as a tree decomposition, you can think of, for a node, you can say that the back of this node is the union of the boundaries corresponding to edges incident to that node. Okay, so that's the back of the node. So, and we want to maintain that these backs are reasonably small. Okay, at this point we don't want yet a constant approximation, but what we can say, we want to maintain that the degree of this tree decomposition, this branch decomposition, is at most 2 to the O of k. So this gives, with this back construction, this gives a tree decomposition with 2 to the O of k, which in a later post-processing step will be optimized to like just O of k. And we also want to maintain, just for the things that are quite intuitive in the context of dynamic trees, the depth of this branch decomposition should be logarithmic. Okay, so these are the invariants that we maintain. So what's now the key thing that we can, while maintaining these invariants, we can actually implement two kind of local rotations. So first rotation is contraction. So when we have an edge of this branch decomposition, what we can do, we can contract this edge, like in this picture, we're contracting this red edge, and this clearly it maintains downwards well linkness, but it increases the degree. Okay. And then we have another operation. So this is a more non-trivial operation. It's splitting. We have that whenever we have a node with sufficiently high degree, so something like larger than 2 to the O of k, what we can do, we can locally split it to multiple nodes. Like in this picture, we have this red node of degree 4, and then we can split it to like 2 nodes, the red node itself and an additional child node here. So this is how we can control the degree, and this is like a lemma that this splitting can be done always so that downwards well linkness is maintained, and you can actually do the splitting in a completely local way, just looking at the node, and you can figure out how to split it like this. So this is really efficient and like a local thing in the branch decomposition, and we also in the splitting we can do some additional stuff, like we can choose a set of, say, at most 3 children that will not drop deeper in this picture when we split a node. Okay, and this is kind of essential for using these local rotations for maintaining the tree decomposition, the branch decomposition. Yeah. Now what happens in the algorithm is we just use these two local rotations, this contraction rotation and this splitting rotation to implement the split tree like dynamic algorithm. And like everything kind of works out. We can use a potential function that has like a factor for the degree of the node, or the number of children. Actually, this should be this should be oh yeah, it's degree. It's not number of children, but it's degree because it's -2 times the logarithm of the subtree size. So this is like the splay potential with some degree factor, and like splay tree kind of stuff then works out. And how the algorithm in the end works, okay, we have to somehow implement like inserting and deleting edges from the structure. So for this, we have additional self loops on the vertices. And then if we want to insert an edge UV between vertex U and V, we first rotate the self loops U and V to the root. And then we can insert UV as another child of the root. And this is like why we do this is that this is nice for keeping all the boundaries well behaved while doing an insertion. Like when everything relevant is in the root, somehow you can do the insertion without touching like the rest of the decomposition at all. And the same thing for deletion of it. You just rotate it to the root and yeah. Yeah, and we maintain this decomposition, which has width to the of k, but then there is you can actually do like a slash post-processing step where like each node can be locally replaced by a tree decomposition with O of k, which gives this final approximation ratio of like 9k. Yeah, that's all that I have time to tell about this algorithm. So in conclusion, we have dynamic Treewidth algorithm with amortized doublet time to the of k log n that maintains a 9 approximately optimal tree decomposition of a dynamic graph of Treewidth at most k. And it can also maintain these dynamic programming schemes on tree decomposition. And yeah, there are several applications of dynamic Treewidth that this can help, like graph minor testing and dynamic kernelization. Let me lastly mention some open problems. So first is this still amortized. So can we do instead worst case? Another one is can we rule out a running time like this is running time like f of k times log n? Can we rule out running time f of k plus O of log n? To me, it sounds like we shouldn't be able to do this kind of update time. So can we show a lower bound? And the last one is can this approximation ratio of 9 be improved? So it seems that you cannot, if you want to explicitly maintain a tree decomposition, you cannot do better than 3. I think I sketched the proof of this myself. But yeah, there's some gap still between 3 and 9. Yeah. So that's all. Thanks.